All
All right.
right. It's all
All right.
yours.
Thank you. And guys, maybe that's a little bit different from what we keep presenting, but Flavio and Yuri thought that could be a good topic to go around. It's about rate adaptation algorithms, and more precisely, how does your phone, your tablet decide what data rate to use when you're connected into a Wi-Fi network? And the reason why this is coming often is because typically people try to design networks. And when they do, we typically tell them, okay, if you want to design your cell, the right size of the cell is not too big. Do not put your access point to max power, because typically your phones are not going to be as powerful as the access point. These things are going to be 11 to 14 dBm, whatever the brand, it's about the same power. The AP can go all the way up to 20 or 30 dBm. So if you have, that kind of structure, there will be a big asymmetry where the AP will be heard and the client will not be heard back. So set the AP power to about the same as your client. And then once you have that, try to work with a data rate that you allow on the access point to make the cell small to fit your requirements. And when we say that, we say, okay, best thing to do there is to say, suppose you're going to support voice. A good RSSI value at the edge of the cell is going to be about minus 65, minus 67 dBm. If you support data, we say, okay, you can go to minus 70, 72, but let's look at voice to make it simple. So we say, okay, you move away from the AP, you get to the point where you have minus 65, minus 67 dBm, and you know that at that physical point in space, this is where the edge of the cell should be, which means that there should be another access point with about the same signal on the other side. So as your client keeps moving, the client will jump to the next AP. However, the client doesn't have any reason to roam there just because you stand there and it's minus 67. In fact, those devices have algorithms that kick in at minus 70, minus 75, depending on how the experience to the previous AP is. So we say what you want to do is at that point, try to remove some low data rates. And if you remove them, what happens is as the client will go past that point, it will start losing connectivity to the AP a little bit beyond that point, and that will force the client to start looking for a better AP. So the client will jump there to the next AP instead of waiting to be far and having a lot of losses and be below the next AP. So that's way too late. So if you want to, set that transition by the middle, you want to remove those basic or mandatory data rates from your AP so as to encourage your client to start looking. And we say, well, there are two types of rates, and there are three possible rules. The three possible rules are what you see on the screen for the mandatory basic rates, which are the BG rate, the 1, 2, 5, 5, 11, but in the G and A family, the 6, 9, 12, etc., up to 54. Those are what we call legacy rates, but these can be set to disabled. You drop them off, and that means the access point doesn't do them, and it advertises that it doesn't do them. Or they can be supported, which means the AP does the rate, but if the client doesn't do it, it's okay. Or mandatory. And mandatory is what is useful here, because all the broadcasts of the AP are sent at the lowest mandatory rate, which means that if you do what we see on the slide here, the first allowed rate is also the first mandatory rate, 12 megabit per second. The beacons are going to be sent, the probe responses are going to be sent at 12 megabit per second, which means that when the client is going to move away from that cell by the middle, if by that time, it still hears the beacons good, but if it continues, it will start losing those beacons or probe responses because, it will be beyond the point where those rates are easy to be demodulated. And that will force the client to say, oh, I'm losing some packets from the AP, I need to look for a better AP. And that's how you push the client to the next AP. However, we also say, do not waste your time disabling the equivalent 11N, 11AC, 11AX rates, the 6.5, 13 maybe. Don't waste your time there. And the reason why is because in the WPA and WPA2 tests, there is a test of speed in the Wi-Fi Alliance where if the AP says, I'm doing 6 megabit per second, they test that the client doesn't try 6 megabit per second because the AP doesn't do it. So this is tested. but there's nothing that tests the new rates, N, AC, or AX, which means that if the AP doesn't support 6.5, then the client, it doesn't advertise 6.5, the client doesn't care. It can still talk to the AP at 6.5. There's nothing that says the client shouldn't do it. So we typically say, you can work on these mandatory rates, the legacy rates, don't work on the new ones. And when we have all these advice sets, typically people who design network come back and say, yeah, but that's a general rule. What about this particular device I have in my network? Could be this guy could be an Android of any type. How do I know what is the data rate that matches that minus 65 thing you're talking about? Because if I knew that, then I could not only disable 6.9 as you show it here, but I could also disable the others. Right to the point where this device is going to be talking at some speed, and that would be a good design. And then, of course, I can also disable the N and AC and AX rates that work along with that, because I know that anyway, beyond that point, the client is not going to try to use the upper rates. So it will force the client out. And typically when this question is asked, and it's a very valid question, we say, it's difficult to tell you what rates your client is going to do. Because there are multiple rules and they are combined together in a way that is not easy to sort. And of course, typically people say, you don't know, or you don't want to tell me what's the problem there. And so, Yuri, Flavio, and I thought, okay, maybe it would be useful to share what happens inside the clients, so as to help you understand, why you shouldn't bother, but also if you want to test and know what really happens in the background, how you can test. So this is what we're going to do here. And the first thing we'll do is open the page of the standard ISO 2.11. And if you look at the various clauses, as we say, 11N, 11AC, 11AX. For each of them, you will find somewhere in the clause a table that you see an example of here in the slide, which is the receive sensitivity performance requirements. And what that says is that if you want to say that your system is compliant with, say, 11AC, VHT class 21, for example, then in the absence of noise, well, noise is set to minus 94 dBm in the test, but that's very low noise. So in these conditions, if you receive on the station a signal set to a certain value RSSI, for example, here minus 82, you should be able to demodulate this BPSK 1/2 90% of the time. So if we put the thing the other way around, we say that it means that every device should be able to demodulate a signal received at minus 82 with BPSK and a half, 90% of the time. So, one first thought is to say, well, why don't we use that table then, right? We just say, okay, these are the minimum values. So because the links are supposed to be symmetric, I should assume that if I can receive at minus 82 from the AP, when I speak back to the AP, and if we did the job we said, to put the AP at the same power as a client, well, then the AP is also going to receive at minus 82 because the links are symmetric. So if I receive BPSK half from the AP, well, then the AP should be able to receive back a BPSK half. So I should be setting my data rate based on that basic symmetry of the RF link. Of course, that's a little bit too risky because that there may be some noise and the noise may not be local. They should say it may not be here on the phone, but it may be on the access point because, noise is very local. So you can maybe add what we call a link margin, a link budget, which adds, some buffer. Say, well, just in case there would be some noise, let me add a buffer of 10 dB and assume that the AP is going to get 10 dB less of what I get. And then you could be done with it. However, it's not the way it works. It's not the way it works because it makes a few assumptions that are not true in reality. First is that you are assuming IEEE performances. But in many cases, you have systems that are doing much better than that. For example, if you look at the Cisco AP, at minus 99 dBm, it can demodulate a signal that the IEEE spec says should be there at minus 91. So it's almost 10 dB better than the spec. So you say, well, okay, that's not a big deal. It's not, but you're wasting time, right? By sending something with a low modulation where you could use a much better modulation and be much more efficient with that AP. So by just constraining yourself to the IEEE minimum, you're basically always suboptimal with a good system, and you're just barely good with a normal system. So that assumption that everybody only does the IEEE is a bad assumption. It's a bare minimum assumption. Two, the assumption that there is a link symmetry is also wrong, and I'll show you why in a slide. What works for you on the downstream may not work for you on the upstream. And one of the reasons is that we said we recommend that you put the AP at the same power as the client, but did you? Many people say, I bought that AP does 20 dBm, I'm going to put that AP at 20 dBm. So in that case, the symmetry is broken, and the assumption that what you see on the AP down or from the AP down is what the AP will get on the way up is not necessarily true. So that is an assumption that is poor. And it's more complicated because of what we call a locality, and that's what you see on the right side. Here, it's an experiment we've done where we've been measuring the signal from the client to the AP and the signal from the AP to the client. And we've been drawing the map. And typically what we show in the heat maps on those maps, if you've been using Cisco Prime Infrastructure, DNSC, DNS Spaces, etc., when we show the AP and when we show the heat map, what we show is the expectation of how far the signal will go at what strength based on the assumption of the environment as we understand it from the AP level. But unless we have an explicit feedback from the client, it's difficult for us to know exactly how a client would hear it. So what we did here in this drawing is take an iPhone 11 and get a system that we have with Apple, where when they associate, they send us back a reading of how they heard the AP. And then we did a spiral around the access point, a spiral going from a small to larger. And every 50 centimeters, we've collected the signal. And that allowed us to draw this map. And you see this interesting red and orange zone there. There is, in fact, a metallic pillar on this floor. And from the AP heat map as we project it, nothing special happens. But we actually use a client, and you walk right behind this pillar. Of course, you have a drop in signal. And that means that if you were to use the default, AP, I hear you, I am going to answer back at the same rate, that would not work in this location. So you would be losing signal. And of course, it's just a pillar. It's very small, and that's why I show you this there, because if it's anything bigger, a big printer, some cubicle, some furniture, you can have a multiplicity of those issues all around the access point. So this idea that you have symmetry and that the power is the same is typically wrong. So it's a bad idea to start from that. And also what you see on the left part of the slide is that at any given signal, you have a choice. Suppose that the AP runs 80 megahertz wide signal, and then you have a -68 signal from the AP. Well, you could choose quite a few types of signals. You could choose 54 megs. You could choose different MCSs, and it may be obvious to choose that. If you can choose between 80 megahertz one stream and 20 megahertz one stream, well, obviously you would be sending more at 80 megahertz. So you would think, okay, I'm going to use 80. That's easy. But if you have the choice between one stream at 80 megahertz or two streams at 40, which one would be best? Well, it's not that obvious anymore, is it? So as you continue having all these possible mixes between the various technologies, it becomes fairly complicated to know which one is best. And it's not because the AP chose one system that you should choose the same system on the way back. So all these makes that using the IEEE as a book source for your choice of modulation and encoding scheme or data rates is typically a bad idea. You need something a bit more intelligent. In fact, you need to think of the problem just from the client standpoint. And you need to think, this is what I need to do. First, I need to pick a rate to start from. And we'll go on an example how this is done. Then, every time I speak to the AP, I need to know which one is the best rate. So I'm going to pick that best rate, and you need to know how it is the best rate. And we'll see how that's done as well. Once you pick up the best rate, you need to check if it's working. You'll send frames with that. And of course, if they get acknowledged, it's a good rate. But what if they fail? Then if they fail, you need to have a plan B saying, okay, if I have too many failures, and oh, by the way, what is how many too many failures? Is that 1? Is that 3? Is that 15? You also need to decide that. So we'll see together how this is done. And once you get beyond, that number of failures that you think is the right number, what do you do next? Well, you need to find a second best rate, or you need to have a plan B and a plan C and maybe a plan D. But at the same time, you cannot, rate shift down, from say 54 to 48, from 48 to 36, and so on, in a scaling way, because otherwise, you may have a sudden drop, and you may be failing and wasting a lot of time retrying on different rates that are not going to work. So you need to be efficient in your plan B and your plan C, so that you can jump to something that you know for sure is going to work, so that you can empty your buffer without, before scratching your head and then say, okay, what is the next best rate there? So, in some ways, you have to pick the best rate, find the right retry rate, find the best plan B, and plan C, etc. And then as you keep moving, remember those choices somehow, so that you can come back and pick up the best rate as soon as it's possible. But at the same time, not clinging in on the memory of the past, because if you move behind, a piece of furniture or behind a wall, what was working 5 seconds ago is not working anymore. So you want to remember the past some, but not too much. So, you have to keep learning the new conditions. These are all your requirements. And, I'm not the first one to say this. In fact, in the academia, as we say, this has been a problem for the last 40 years now. Yeah, 40 years, way before 802.11. Right at the beginning of modulations in the unlicensed scheme in the 1980s, people have started saying, how do I choose a rate? And there has been, as you see here, multiple exchanges and multiple theories on what would be the best rate. What I'm going to cover with you is the most famous of those, and that's the one you see on the upper right, Minstrel. Why? Because it was the first one in the early 2000s for Wi-Fi specifically to be published and made available to the general public and to the research community. And because of that, it's been extensively studied, extensively modified as well to be improved. And today it's the reference behavior. And I'll come back on that at the end of this session, but it's likely that whatever phone you have or whatever tablet you have or laptop, unless it's Intel, but if it's any other brand, I'll show you more on that also, it's likely to use somehow Minstrel with a variant of it. So what is this minstrel? It's called minstrel. I don't know if you're familiar with the English term. Minstrel, minestrel is those middle-aged wandering singers. They would go from castle to castle, and they would trade their art, singing a song for money, and of course food and bedding, and then they would go to the next castle. And the logic there is that they could go to multiple castles. So after having some experience with this work, they would probably know which castles are good food, good money, good bedding maybe, and which ones are not the best. So what they would end up doing is picking up the best castles and then ignoring the worst one. So they gave that name to that algorithm, saying we're going to do the same for these data rates or MCSs. We're going to experiment with those data rates, pick the best one. Once we have the best one, we're going to stick to it, come back as often as we can. We get invited there, and if we cannot go there, we'll go to the second best, and so on. But of course, as we keep having gigs, from castles to castle, we'll update our list of good food, good bedding, good lord, etc. So that's the idea. So how does that work? It's a bit complicated. So what I'm going to do is to go step by step, so we together build an understanding of the logic. And once we have this understanding, I may be undoing some things I'm doing at the beginning, but you will see that it will make sense why I've gone through that steps first. So of course, the first time you associate with the access points, everything works at minimum mandatory rate, right? You send your beacons probe requests at 6 megabit per second most of the time. You get responses at 6 megabit per second. So there is not much logic there that can help you find the best rates. But you already have a signal from the access point, so you need to be able to pick up the first rate to start from, and then start learning from there. So that means you will use three components as you start talking with the access point. First, a choice of the rate. How do you choose the best rate at what time? Two, how do you learn how many times do we try? You need to learn that dynamically as well. And then you'll need to run some stats, to compile these two together into a single logic. So let's get started. You are going to associate to the AP, and the first thing you want to do is to pick up the first rate. One thing you can do, which is very logical, is to organize your rates into buckets, groups of rates that work together. For example, everything which is one stream, 20 megahertz. That's one group. Everything which is 2 streams, 80 megahertz, for example, that could be another group. So you're going to create buckets of things that have the same stream count and the same channel width count. Okay. So you have your different data rates in those buckets. Of course, because of the association response from the AP and because of the probe response from the AP, you know which of these buckets the access point is going to support. For example, if the AP is running at 40 megahertz, anything which is 80, all these buckets, you can put them on the shelf. You're not going to use them. So you're going to only retain those buckets that match what the access point says you can do. Then you want to pick out of these possible buckets, those rates are going to be the best. So, you can go in the SemLogic Avator 2.11 there and say, okay, let me start with a conservative logic and say, from the signal from the probe response from the AP, I can assume that the AP can speak at that power. So I can, if I speak back to that AP, if I take this link budget, for example, of 10 dB, we should be able to communicate with the AP. So you could, think of that logic and going through different rates, different buckets available in what buckets are left and say, okay, all these rates in that bucket are possible. In this bucket, all these rates are possible. And you have that way a short list of rates you can use. Then what you want to do is to pick the best rate. And of course, the best rate, you can think, what is the best rate? It's probably the rate that allows you to send the maximum amount of data in the minimum amount of time. And that is because you don't want to take too much airtime, and two, you don't want to consume too much battery. So what you can do then is, out of this short list, do a quick computation and say, if I send two spatial stream at 40 megahertz, how many bytes can I send in one frame? If I send one stream at 80 megahertz, how many bytes can I send? And how much airtime do I consume to do that? And then you pick up the one that gives you the lowest amount of time per bytes. You do a math, bytes per time, you divide that and you say, okay, the best ratio bytes over time is going to be rate ABC. Let's start with this one. So that could be a good start. Thing is that, of course, it's the first attempt. You have no idea if this is going to work, right? So what you want to do is to, on one hand, help the user. And the user is me. I'm browsing something, so my packets need to go, right? So you don't want to spend your time doing experiments. You want to be efficient. But at the same time, you know that you want to learn the best rate. So you have to try if you want to be successful. So what Minstrel does is that it says, okay, let's divide the time into two types of periods. One period that we'll call the sampling period. In the sampling period, and that's 100 millisecond long, I'm going to try different rates there. And then I'll find which rate is best. And then at the end of that period, because many of them may be failing, I'm going to switch to a non-sampling period, which is also 100 milliseconds, during which I'm going to have my job to empty the buffer as fast as I can. And once that's done, based on the rates I learned before, which are the best, I'm going to empty my buffer. And once the 100 millisecond of non-sampling is done, if my buffer is empty, then I can switch back into another sampling period of 100 millisecond, learn maybe what has changed here since my last experiments, 100 milliseconds before, then pick up again the best rates, and then go back into the non-sampling period. So what is interesting is that alternative, right? You're changing between trying time and time where you don't try, you just empty the buffer. So during the experiment period, the sampling period, what you're going to do really is to try rates at random. Again, there is a small, star, at the end, say, wait, we'll talk more about this in a couple of slides, because it's not entirely random, really. But again, we're building our way there. Let's say for now it's random. So you have the possible rates, you have these possible buckets, you just pick up at random in any bucket a rate, and then you send the packet out with that rate. And then, of course, if the rate is pretty efficient, or if it's slow enough that the MCS works well, you should get an acknowledgement from the AP. Good, this rate is working. So you pick up another random rate, and then you start sending at that rate. Successful again, that one is working, check. Pick up another rate and you try again. And of course, as you do so, sometimes you'll pick up a rate and the AP is not going to answer, no acknowledgement. So here you're going to say, why did it fail? Did it fail because there was a collision, somebody on the other side of the cell sent at the same time? Or is it because that my rate is a problem? It's too fast for where I am to the AP. And really, you cannot tell, right, from one single packet. So you're going to retry that packet a certain number of times. And at the beginning, you don't know how many times you should be retrying. So let's say you have a fixed number to start with. Let's say it's 3. So you try 3 times, the AP doesn't respond. Say, okay, that rate is not working where I am. Fine, I'm putting this in the red list, not working. And then you continue picking up other rates. So you see that as you do this, statistically, if you pick up at random, you should, half the time pick up some fast rates, half the time pick up some slower rates. So there is a good chance that half of the time, your packet is going to make it to the access point, and half of the time, maybe the packet is not going to make it to the AP. In which case, okay, then you have to retry a few times, and then you pick up another rate. A good chance it's going to be a slower rate if the one you were failing on is a fast one, and this one is going to work. But it may be that you keep picking up fast rates because it's random, right? So there is a reason why it would be very well distributed. So it may be that as you keep trying, you may end up this sampling period with failures over failures over failures. And that's why we say at the end of that sampling period, you switch to that num sampling and say, okay, from the rates I've gotten, which ones were the best? Try this one. And if that best rate is not working, try the next best. And if you don't have, this best second one, you're going to pick up a third one, which we call is the most robust one. But what does it mean, a good rate? The way Minstrel understands this rate is what we said before. The amount of bytes you can send per unit of time. But it's a little bit more complicated because now that we're building our way up, let's look at that again. It's maybe true now, right? If I'm using, of course, 80 megahertz one stream, it's always better than 40 megahertz one stream because I'm going to be sending more bytes, per unit of time at 80 than at 40, twice as many. But from the table that we had at the beginning, that the RSSI you need to send at 80 is a bit higher than the RSSI you need to send at 40. So the conditions for 80 are not the same as the conditions for 40. They are more difficult, more stringent. So what you want to do is to pick up the best rates, but also see if that rate is actually working for you. So what you're going to do is to look at two things. One is what we call the FLR, which is the frame loss rate. That's easy, right? It's just saying if you send, you fail, you resend, it works. Well, your failure rate is 50%, right? The first one was fail, the second one was a success. Why did it fail the first time? I don't know. Maybe collisions, I don't know. And I don't care really. What I'm measuring is over time, what is the success rate of that rate? And there may be collisions sometimes, but the collision should be about the same for all the rates, right? There is no reason you collide more at 80 than at 20 megahertz. So on average, if you keep trying different rates of different channel sizes over your sampling period, the collision rate should be maybe 10%, 15%, I don't know, but it should be about the same for all the rates. So that should not impact too much the FLR in that it should be about the same for all the rates. However, if you hit a rate which needs better condition, better RSSI, and you're right at the limit of what you have there to achieve this rate, then more often than the other rates, when you try this rate, you're going to fail because more often the AP will say, I can't really demodulate that. There's not enough signal for me to demodulate. So by using the FLR, you're going to start seeing those rates which are super fast, but you're not in a place where you can really use those. They are failing more than the others. So the FLR is the first good metric. The second one is the more complicated one, and that's what we call UNA at the bottom of the slide, exponential weighted moving average. So what this is really is just a memory of the past. You've been trying those rates previously, maybe in the same sampling window because you try very fast. So maybe you try a few times the same rate, or maybe you did that in previous sampling windows. And what UNA wants to do is to remember what happened. So what it does, it's going to choose what we call a weight factor, lambda. And that's how much you want to remember the past, so to speak. And then what you're going to do is to say, I'm going to affect this lambda, that memory factor to the FLR, my frame loss rate. And I do it in a way which is a little bit weird that you see at the bottom where I say, I'm going to do 1 minus lambda time the frame loss rate of this window. And then I'm going to also add the 1 minus lambda time the previous FLR of the previous window, but I'm going to square it. And then if I have 2 windows ago, I've done that before as well. I'm going to do add 1 minus lambda times the third window cubed. And of course, if you look at the equation, you say, what? Why are you doing this? What's the logic? Well, logic is about memory of the past. Let me give you an example to help you understand what the structure is here. So let's look on the left side first. Imagine, okay, we take lambda as 0.8. Number doesn't matter, right? It's just how much memory matters to you. And then suppose that during this, and we take one specific data rate. Which one doesn't matter. What matters is logic on how you compute the memory. So for that data rate, in that current window where you're trying the sampling window, your loss rate is about 10%, on the left side. And then in the previous sampling window, your loss rate for this one was 40%. And let's say, 2 windows ago, it was 80%. So, it's good now, you have only 10% losses. It was kind of bad before and super bad even before. And that's, a few hundred milliseconds ago. So how good is that rate for you? Well, if you were just to compute this lambda times your loss rate, you would get 0.8 divided by 2, 0.08, which is okay. That's not giving you a good number. But if you start focusing on what the rate was before and what it was before and what it was before, and you keep doing this, I'm showing you just windows, but imagine you can have a bunch of windows before, then you see that in the end you say, oh, my score for that rate is 0.288. So it is not that you have 20%, it's not 0.2, right? You remember that before you had a higher loss than that. So 0.2 would be a fairly good result because you're using lambda 0.8 and you have a 10% loss rate. So as you do 1 minus lambda, it gets to 20%. So you say, okay, I'm getting a not too bad number, but because you also account for the previous losses, your UNA loss goes higher because you remember it was not that good before. So instead of being 0.2, you end up with a 0. Close to 3 or 0.288. So that makes that with that system, you do remember that things were not as good as they were now. It also works the other direction. Let's take the other opposite direction. Suppose that now your loss rate is 80%. So that's super high, right? But then before it was 40%, which was not very good. But before it was very good, 10%. So what do you want to remember? So do you want to remember that loss rate is 0.8? Well, yeah, because that's the conditions now, but it wasn't always the case. Maybe you're just walking behind that pillar I'm talking about. So you may want to remember that that rate, although is not working in this one window, in the previous windows was pretty good to you. So, maybe there is something very temporal, very local that you're experiencing that makes that this rate doesn't work now, but because it was working before, it's not as bad as it looks. So when you want to compute the loss for that, doing the same math as you see on the right side, you end up saying, yeah, really my UNA loss here is 0.722. It's not 80%, it's 72%. So you see logic by using that UNA and accounting for what happened before. What you're effectively doing is computing the loss for this window, but you're also remembering how the previous windows were making things slightly different, maybe better, maybe worse. So what that does is that Minstrel not only focuses heavily on the current window, it also remembers the previous windows. But as the window go farther in the past, their importance gets less, because as you see, as we do 0 point something and we square it, cube it, and power of 4 and so on, 0 point something to a power gets a smaller number than the 0 dot something number itself. So as you keep doing this, square, cube, 4, etc., that number becomes smaller and smaller and smaller, which means that as you add it, it doesn't influence as much as the recent numbers, the final metric, which means that as the window is farther away in the past, your memory of it, gets away. And that's a good life lesson, right? You want to remember what happens now, right? That's your present. You want to remember somehow what happened in a few times of your past, but very far away things, people have changed, you as well. So you may want to start forgetting old stuff. That's the logic for you now. Okay, So now you have this loss value. So what we're going to do this is based on the the frame loss rates and the UNA weighting of that loss rates. You're going to have what they call the throughput, which is the ability with that rate to send data. And if I go back to my example at the beginning, I was telling you, oh, you just look at the number of bytes you can send divided by the airtime. Remember, I was saying that's the first choice. Well, now let's make things a little bit more complicated. We say, yeah, you want to do the amount of bytes you can send divided by the airtime, but you also want to account how many times you succeed doing that. So for each of those rates, you're going to multiply by the UNA value, which means that if you say, I can send 2 bytes in 1 second, but it works only 80% of the time because your UNA is 0.8. You multiply this 2 divided by 1, by 0.8 to give you the real throughput, because 20% of the times you're not going to send anything. 80% of the time you're going to send something. So what Minstrel does is, for each of these rates that you've tried, each of these rates for which you have computed the UNA value, what you're going to do is to apply the UNA weight to that very simple metric of number of bytes per unit of time to see how really efficient that rate is. And you see that's pretty cool, because as you go from one sampling window to the next one, that UNA weight is going to be changing again. So the efficiency of that rate is going to be going up or down depending on the conditions, but you're still going to have those rates that give you, the max amount of bytes per second that are going to be considered first because they are more efficient. But their real efficiency is how many percent of the time they work. That's going to also tell you if you should use them, or if you should something that a little bit less efficient, but because it works more often, it's going to be a better successful rate for you. So that's the throughput score, as we call it. Okay, so you see that's a bit more complicated than just bytes per time, but it's also more efficient, and it's also constantly learning as you keep going into these sampling windows, because now you have this moving average of efficiency of those rates that are combined with all these rates' ability to transmit a lot of bytes in a little amount of seconds. What we're still missing there is the retry chain. If you pick a rate and the rate works for you, and you send a frame and it doesn't work, how many times do you retry? And we said at the beginning, let's make things simple and say, let's say you retry 3 times. Yeah, it's not the way it works either. It's a bit more complicated than that, but now we're ready to go into that complexity. In fact, what Minstrel does is that it defines a retry window in terms of time. And this is super important. If you pause a second to think about it, you say, if I'm speaking at, say, 150 megabit per second, how long does it take for me to send a frame? Okay, 200 microseconds? Fine. If I'm speaking at 1 megabit per second, how long does it take me to send the same frame? 1 milliseconds, which is 5 times more, right? So you say, if I want to retry 150 megabit per second speed, how many times should I retry? Well, you can retry 5 times that thing in the time it takes you to just send one attempt at 1 megabit per second. So if your rate is faster, it would make sense that you may want to retry it more times because it doesn't cost much time. But if the rate is super slow, you don't want to retry it too many times, because retrying that one consumes a lot of time. So what Minstrel does is to say, I'm not going to give you a retry count, like try 3 times. I'm going to give you a retry window. And that window, depending on the protocol, it used to be 24 milliseconds. Now it's 79 milliseconds. So they're going to say, okay, I'm going to give you a retry window of 79 milliseconds. But I don't know if you want to consume it all, because if your data rate fails all the time, you don't need to retry it 15 times and consume the entire 79 milliseconds to know it's failing. You could have guessed that from first go, right? You have that rate, it fails 90% of the time. You try it once, you try it twice, it's failing. I know it's failing 90% of the time. What are the chances that in the end, if you keep trying for 79 milliseconds, it will end up saying, okay, it's working now? It's very small. Whereas if your rate is working all the time, and then you try, and it fails, you say, well, that's unusual. Usually this rate is good for me. Let me try again, and then again, and again, because it should work. So the logic of MinSphere is to say, let's take this UNA and FLR and try to apply it here as well as a coefficient to my 79 millisecond window. So if my success rate of my is 80%, let's
Hey, Jerome, can you hear us? Can you hear us? I think we lost your audio. Not sure what happened, but I guess we lost your audio. Okay, acho que ele está se reconectando aqui, pessoal, só um minutinho.
All right, let's see if it's better now. Am I
Yeah,
back?
it's back. Yeah, thank you.
All
Can you
right.
share your slides again?
Sure, yeah. How long ago did you lose it?
No, I think 2 to 3 seconds, not much more than that.
All right, so it's mysterious. Sorry for that, guys. All right, we go back there. Beautiful. Thank you, Flavio.
Yeah, you were explaining, the window. You don't have to wait until the last of the 75 milliseconds to see that a rate is not a good rate because it's failing multiple times already.
Exactly. Thank you. Thank you very much. So you see, by applying this UNA not only to the success rates, you pick up the rate that works best for you, but to the retry chain, you also don't waste time retrying a rate that you know is typically failing for you anyway. So you are more efficient there as well. So that makes that when we are here, we have the structure where we say you're going to use that learning in the sampling window. Then once you have this learning, at the end, you will have a list of rates, each of them having a sort of a theoretical max throughput number of bytes per second, weighted down by this UNA value. But then you'll be sorting those rates, the ones that give you the best bang for your buck, the ones that will give you, despite UNA, the best throughput out. And that will be your first rate. And then you're going to pick the second best. That will be the second best rate. And then you're going to go down the chain and you're going to find if there is a rate that works all the time, the one that has 100% success. If you find it on the way down, right, you pick the fastest rate, which has 100% success rate. And that's your plan C. If you don't find a rate that has 100% success, you go down the chain until you find the one which has the highest success percentage. And once you have that, this is the third rate. So once you have made that learning into the sampling window, you go into the non-sampling window, use the top best rate, and boom, 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 use that one. And then if it fails, you start retrying again based on this window 79 millisecond times UNA, certain amount of time. And if you keep failing there, then you switch to the second best rate, C2, your plan B. And then you try this one. And again, if you fail there, then you directly jump to the one that always works, the 100% success rate, because your job there is not to be fancy. You want to empty your buffer. So you pick that rate that works all the time. And that continues until you get to the end of the non-sampling window. And at the end of which, if you have spent more than 100 seconds there, you have emptied your buffer, and it's been more than 100 milliseconds, you can switch back to a sampling window where you try relearning again. So you see, in the end, logic is a bit more complex than what we were saying at the beginning, right? We're saying you can pick up a rate that matches the RSSI of the AP, and then you can also, pick up the best data rate. Well, in fact, most of the time they don't do that. What they just do is that they connect to the AP and they immediately enter a sampling window, which means that they immediately stop random rates and they start, measuring which ones work, which ones don't work, compute UNA, and try to use UNA to dampen the validity of that rate and the retry value for that rate. So you're going to start the sampling window, do that determination, and of course, you're not failing all the time, right? Some will fail, some will not. And as you keep going from one rate to the other, overall, some packets are going to make it out from the station to the AP. And then at some point, you'll have your end of your sampling window. You may have some packets left in your buffer, and then you switch into your non-sampling window, pick up the best rate, try to empty the buffer. If it fails, pick the second one, try to empty the buffer, pick the strongest one if you have to empty the buffer and until the rest of the non-sampling window, and then go back again. So you see that's logic. It's fairly logical. And of course, from this, you say, okay, so what data rate should I disable if I am at the edge of the cell, my 65 dBm? I don't know, right? Because you're going to be learning all the time. You're going to be adapting to the conditions. So depending on how your travel was from the center of the cell, where maybe you were, to the edge of the cell, what you will know about possible rates will be very different from if you are just walking at the edge of the cell. So it's not very easy to say, well, there's a hard number you can use as a good reference point to decide which rates you should be disabling and which rate you should be keeping on. And by the way, what about your station? I was telling you that Minstrel is a very well-studied system, but it's not necessarily the one you're using. In fact, there have been multiple variations out of Minstrel. Some of them are interesting to mention. One of them is Mira. Mira stands for MIMO Aware Rate Adaptation. What it does here is that it's going to think that this idea of trying at random is not necessarily the best one. So it's going to start the best, and then of course maybe it fails. So it's going to start low, very low, and that's probably going to succeed. So it's going to jump to second best, and then going second low, and it's going to zigzag its way to the best rate. So they thought that by using this logic, you have a better structure of deciding which ones of the rate should be the best one. So you see it's a small variation from Minstrel, but it's important because they have a different zigzaggy structure depending on if you're using multi-user, MIMO, or if you are multiple input and outputs, MIMO, or if you're using blocks. So that's interesting variations. Another one interesting is Ramas. If you work in the banking industry, you'll like this one. What they do is that say, forget those buckets, I give you budgets. You have these MCSs 1, 2, 3 to 9, and then I'm going to give you budget where say you have extra bonus if you use 2 streams, you have extra bonus if you expand to 40, and what they try to do is to maximize their budget consumption. Spend as much as they can, and if they fail, of course, their budget shrinks because the failure of 40 megahertz makes that they cannot spend at 40 anymore. They have to go down to 20. So you see, it's a slightly different approach. Another one which is interesting is Damaisus, which is one of the giants in the Greek mythology. They have this idea of Minstrel, but they say, with 11AX now, we have the OBS SPD, when you are at the edge of the cell and maybe you're hearing the neighboring cell and you want to reduce your power so as not to disrupt operations in the other cell. At the same time, you want to ignore them and so on. So they incorporate all that logic into a sort of advanced Minstrel. So, Minstrel is the most classical one because it was the first one to be open, but it's likely that your phone is using some derivation of Minstrel. Very commonly, developers from any vendor, they start from Minstrel, then they start cooking some home improvements based on their logic or politics. Depends very much on how they view the world and what the station should be allowed to do, and then they improve Minstrel. So in the end, it's very difficult to know if your device is using pure Minstrel. What is sure is that it's probably not using pure Minstrel. How far from Minstrel? Well, if you want, you can test it. And a nice way to test it is to experiment, just make a rate fail. An easy way to do this, for example, is to take a box. If you have something like a metallic box, something a little bit heavy, put the phone inside, put an access point above, and let the phone for like a few minutes until it forgets the path very far away. Connect to the AP and use the fastest rate, and then you close the lid of the box. And of course, that's going to kill the communication. That's what you see here downhill, and then you reopen the box, and then you look at how long the device makes to relearn, how is the relearn process, and from that you can infer if it's going up and down, if it's a Myra, if it's going up in sort of stages like you see here, that's a clean Minstrel. If it's accounting for the power, you'll see some a slightly different logic. If it's If it's a MIMO structure, it's going to try to inflate to 40, and to 20, it's going to try to the inflation and then revert back as it fails. So you can go to the previous slide that I will share, and then you can find what kind of logic your device is. But in the end, you're just looking at one device, right? It's very likely that every vendor has a different logic. It depends very much on what chipset they are using, right? If they're using Broadcom or Qualcomm, they have typically some low-level chipset driver there. But then any vendor, Samsung, Apple, and the others, they have a say into what they want there. So they will also dictate some behavior on top of the low-level driver behavior that will make it some changes. So it's likely that you will see family of behaviors, but many vendors will have a slightly different behavior. So that makes in the end you cannot really decide what is the right rate at which you should stop your cell. Besides doing these basic data rates, 12 megabit per second maybe, or 24 megabit per second. But at least I hope that at the end of this presentation you have a better understanding of the magic of what happened inside. Some people say this presentation is a Sigmund Freud of what happens inside the phone, but that's pretty much what I wanted to share with Yuri and Flavio. We thought should be useful to you, to have at least this logic. And if you want to go further, of course, reach out to any of the three of us. But also what you can do is to read these documents there. It's a good bedtime reading. The one at the top gives you a very good view of the different academia of ways of doing this structure. And the one below gives you also some performance metrics against each other of them. So you can see in which conditions they work. One works better than the other. I know there is not absolute winner, right? Depends if you're an enterprise environment, home environment, if you're moving a lot or not. The algorithm is going to behave slightly differently based on those changing conditions. And of course, that makes that vendors typically implement the algorithm for the environment where they think you're most likely to be. If you buy an expensive toy, it's likely they will think you are an enterprise environment and changing environments all the time. If you buy a cheaper one, they will assume a home environment, a fairly stable condition, so their optimization logic might be slightly different. All right, let me pause there and see if we have any questions we can address.
Hey, John, we have some questions here in the YouTube. Let me get here. Basically, some questions regarding the MCS. So what is it? You said that there's a supported basic rates for like the cell edge. So there's any requirements or best bets, I would say, for MCS, like high bandwidth? Do you suggest anything, or normally don't touch that, just keep the basics? How do you think?
Yeah, great point. I would think that you should touch the basic ones, 6 megabit, 9 megabits, and maybe set the first one to 12 megabit per second. If you do voice 65 megabit per second, I would do that. Anything which is 40, 80, I would use automatic. And anything which is one stream, two stream, etc., I will leave that to automatic because there are too many variations of clients and client conditions for it not to be risky. What you risk doing if you touch those is to prevent your AP from answering at a rate at which your client is talking. So the client talks to the AP, but the AP cannot answer at that rate. So you create a sort of asymmetry. So yeah, I will not touch those.
That makes sense. Let me see. I think that the other one is close to this. Yeah, it's pretty the thing. Do you have another question, Flavio? I know I have a bunch.
I do. So yeah, I took note here. So let me go back. So yeah, the first one, and I think it's related with what you're saying in your last slides. So I'm assuming all of this implementation is kind of a secret sauce of the vendors, so they don't publish what they do, right? So for you to figure it out, you have to test it, or can we find out that somewhere?
Yeah, in fact, the only one that is published is Intel, and thank you, Flavio, because I forgot to mention that. Their algorithm is called HAL, H-A-L. And if you look up HAL Intel on the internet, you'll find a paper that was published in MSwim last year, where they describe exactly how it works. They are the only ones. Everybody else, exactly as you say, you have to test. Close the box, reopen the box, and guess from the behavior what the behavior will be. I'm not recommending though that you do that. guys, because if you do, it will work. But the next time these guys bring a new version of the operating system software, you have to restart because they probably will tune a tiny little thing somewhere that will make it slightly different.
Okay. And this implementation is made from the OS vendor, or in the end of the day, it comes with the chipset and the OS vendor just tweak it?
Yeah, that's interesting. Each chipset vendor, say Broadcom or Qualcomm, they deliver a default behavior, but then they also deliver an SDK. And in the SDK, they have hooks into the retry logic. So, it might be UNA, for example, but you can decide if your lambda is going to be 0.8 or 1, or if you say, I don't care about lambda. So, each vendor is able to tune those. And then when you are a big player like Samsung or Apple, you can go back to the chipset vendor and say, yeah, you don't give me a hook to this part, but I want it to do it this way. And then, of course, you have this influence. If you're smaller, then you just use the SDK to fine-tune the default logic. But just that is enough to completely change the behavior from one phone vendor to the other.
Interesting. Yeah. Oh, very interesting. Do you have anything
we have another question here. Okay. Yeah, I have one more. So considering STA that has not been over the sampling period, as they have the best data rate is not moving. So they are going to run the sample period again, or they're going to keep the sample?
Oh yeah, Diego. Yeah, that's great point. Yeah, in fact, yeah, you run the sampling period anyway because the rate is great, it's working for you, but maybe there is a better one, maybe a faster one. So even if you are the fastest ever, you'll go back to the sampling period and try it again. And that's because we say, in the ideal conditions, it should stay the same, but RF is never idle. It's always changing a little bit. So unless you're in an isolation chamber, if you're in real life, the signal is going to go up and down, so you'll get some failures. So that's why you even if you have 100% success in a non-sampling period, you go back to try it a few more, see if you can adjust to whatever may be changing on you.
Yeah, that makes sense. And of course, the device don't know if it's moving or not, right?
Yeah, nobody tells it that, right? Even the changing RSSI, as you say, could just be the effect of multipath. So you just don't know. Yeah.
Yeah, that makes sense. Do you have another question, Flavio?
Yeah, it's related to that. So when the whole process begins or restarts, it keeps doing that? Or there is some intelligence where the client can learn, maybe based on the BSS, and keep that information somewhere to be used later, or no, it's all the time restarting.
Oh, you're looking at the research right now as we speak, Flavio. Absolutely, thank you for that. Because for now, it's absolutely only in the driver, so it doesn't keep any memory of the BSS or the position, because the position would be playing a role. What more and more vendors are thinking of, if you say, well, we use machine learning, to detect the RSSI and the BSS ID. If we have those two things, yeah, maybe we can make a better choice instead of retrying all the time. But that's just cutting edge research for now. Today it's only in the driver and it's done. It just keeps trying to adapt. Yeah.
Cool.
Yeah, we have another question here from the chat. I think that's the last one. So Diego said, "Hi Jerome, great presentation, very informative. Have you ever heard about AI-based algorithm like neural network? And if it would make sense to have this kind of application for rate selection?"
Yeah, that's spot on. And with Apple coming with their chipset A13, A14, what have you, they have more and more neural network capability inside the device. Because what you want to do is not so much find the next best one; it's to predict how the failure is going to affect your efficiency. So you want to have a machine learning, for example, neural network will tell you if I know this rate is going to work for the next 5 seconds, so I don't need a sampling window anymore. And it's only if I fail in my prediction that I go back to sampling. So yeah, that's cutting edge. For now, this doesn't exist because for now, Broadcom chipset is put into the phone, and that's where things happen. But with that, these research people say, well, you have the operating system above, and you have these hooks into there, so maybe you can feed back and forth and get more intelligence. But that's just starting. We're just at the beginning of that. First papers are being coming this year, so it's very, very new. Yeah.
Wow, it's good to hear that.
Yeah, it's promising field. Yeah, absolutely.
I start to think about getting a new iPhone right now.
Didn't say it was the best one, right?
Yeah. Anyway, I don't have any other questions. Do you have another, Fabio?
No, I think that's it. Yeah.
And
All right.
thank you, Jerome. Always wonderful have you here.
Well, thank you
Everybody
guys
is
for organizing this event. It's a very, very good idea. And apologies for missing emails. I'll continue missing them, and I'll do my best to do my homework better. I need the AI in my mailbox.
You know, next time I'll take my car and go to your home. It's just 5 hours.
Yeah, exactly. Come have dinner. I'll put the mask. Promise.
Okay, I will do that.
All right. Thank you, guys.
All
Take
right,
care.
Tom. Thank you.
Bye
Take
bye.
care.
Bye-bye.